motivating the reason why we are looking at unital channels, let me talk a little bit about measurements. So projective measurements are a form of unital channel. So the point is that suppose I start from a pure state and I do some measurements of some local operator in a projective fashion. Then the cross operators are given by the projectors. And if I think of the channel that is generated by these cross operators, then it is a unital channel. In the sense that if I don't keep track of the measurement outcomes, so this is a entropy increasing channel. So the evolution of a mixed state under this measurement channel will generically lead to a mixed state, the maximally mixed state, which is identity, which harbors no quantumness, right? So one may, at this point, ask like, okay, what about measurement-induced phenomena like measurement-induced phase transitions, or even quantum error correction, or measurement-based quantum computing? The point is, for all these processes, you need to keep track of the measurement outcomes. So you can't forget the measurement outcomes. So at the end of the measurement protocol, you have these trajectories of pure states, and the combination of the information of the probability with which you get the pure state and the entanglement properties of the pure states allow you to get some interesting measurement-induced phenomena. But suppose we forget the measurement outcomes, then the mixed state is a featureless state, at least if I look at the steady state. So this is a natural class of channels for which our restriction to unital quantum channels are relevant. Completely separable mixed state, which is like the identity matrix. Just to demonstrate that, let me show you a small numerical example. So suppose I'm here, time goes to the right. Suppose I start from some initial, not is a product-like state. So in this case, I've just chosen, for future purposes, some dimer-like state, which are bell pairs on nearest neighbor qubits. And now I apply some gates. Say I have some combination of unitaries and some measurements. And suppose I don't restrict myself to, I choose some random circuit like this, and I don't keep track of the measurement outcomes. And now the point is that I want to study the evolution of the mixed state under this channel. So as you know from measurements, there will be trajectories, which will be sampled by some Born probability. But suppose I consider the mixed state, which is the sum over all these trajectories with the Born probabilities. Is the mixed state inherently entangled? So to compute in mixed state entanglement for some partition, I have to look at some mixed state entanglement measures. And one such computable measure, the negativity behave with time. And unsurprisingly, you see that after some order one time, the negativity goes to zero, tangled states. But then after some short time, it just goes to zero, and the mixed state and the steady state done with this channel is the maximally mixed state, which is the identity matrix. But the story changes a lot, and that's one of the the motivations behind this work. Is if I apply measurements which satisfy certain symmetries. So in this case, again, I start with some something like this, and now the measurements are in the singular triplet basis. So it measures 2 qubits and checks whether it's in the singlet or the triplets. So this measurement, it turns out, it respects a global SU2 symmetry of the spin chain, which I'll discuss eventually. But you can imagine this is a restricted version of some measurement. So there's some symmetry structure. And now I can check the same story. I can check, say, half-chain entanglement negativity of the system. So, and what do I get? I see that there is some transient behavior at some short times. This is I'm plotting the half-chain logarithmic negativity of this mixed state as it evolves as a function of time. Okay, there is some transient behavior, but then at some steady state, the entanglement seems to be increasing as I increase my system size. So there is some, as I increase my system from 4 to 14 spins, the steady state entanglement should grow. And if I just naively plot this in some even logarithmic scale, it seems to grow logarithmically with n, where n is the number of qubits. So a priori, this is a bit surprising because this is a measurement channel. We know it's a unital channel, and it should have generically led to the maximally mixed state. which the identity matrix being completely separable, there is no entanglement in it. So what's happening here? Is there any, and it's not only that the entanglement is non-zero, it seems to be also extensive in the sense that as I increase my number of sites, the entanglement seems to be increasing. Also, there is this kind of curious observation that it's growing, seems to be growing logarithmically with n. Is there some, what is the nature of the state? So this is to motivate, all the question that led us to this work is to see if this story generalizes. Is there some structure that I can identify that leads to such entangled steady states? Is this entanglement genuine? We are measuring logarithmic negativity. Is there any operational meaning to this entanglement? And also, I would like to I can ask that how fine-tuned is this example? Does this is it stable under some perturbations and so on? So with this motivation, that's what we study, and I'd like to answer some of these questions in this talk. So before that, maybe let me pause for a bit and ask if there are any questions before I move to the outline of the talk.
I have some questions.
Yes.
So I think you will mention this, but I just want to know it now. Will the results later just be about 1D system, or it doesn't matter?
Right. So it doesn't matter. In fact, we'll show that for any kind of bipartition, these states will have this behavior of this entanglement. So in fact, the state that you get at the end is some permutationally invariant state that has long-range entanglement, but it's not dependent on the dimensionality at all.
I see. Then what about the coefficient in front of the log? Is that 0.5 something significant?
So we will try relate it to the nature of the symmetry that's acting on the system. But it's an interesting and slightly open question if there is some relation to some safety or anything. It's definitely not safety. This is like highly excited, like it's an infinite temperature in some sense, as I'll clarify later. But there might be some interesting relations with other.
Yeah, you said it's related. You said it's related to the symmetry group.
Yes.
Okay.
So at least for this problem, we can predict. We'll show that you can actually predict what will be the prefactor, at least for certain entanglement measures, maybe not negativity. Actually, even negativity, but for definitely some other entanglement entanglement measures, we can predict what will be the prefactor.
Thank you.
Okay. Feel free to pause, and ask any questions if you have. But so let me proceed. So. So this is with that motivation, let me go to the outline of the talk. I want to first talk about the notions of global symmetries and mixed states and quantum channels. Then I'll talk about a result which tells about what are the conditions under which the steady state under these channels are unique. And then the main bulk of the talk will be understanding the entanglement structure of the steady state by looking at some interesting mixed state entanglement measures. And finally, we'll lead to a symmetry-based classification of the entanglement structure of such steady states. And I'll end with some thoughts and ideas about some finite temperature versions of the story. So, so let me go ahead and talk about symmetry in mixed states. So, so we all know about how symmetry acts on pure states. So we have some symmetry group G. Our Hilbert space is typically given by a tensor product of some small irreps of this symmetry. And if the total Hilbert space, this is a tensor product space of say n small irreps, decomposes into a direct sum of some irreducible representation. And that's the state space that's under the symmetry. Let me introduce this notation where I've said that Vj, so J suppose it labels the irrep of my symmetry group G, and the number of times it appears in this tensor product space is called the multiplicity. this is something that will keep coming back. So just let me introduce this notation. So this tells you that how many times is this irrep represented in this tensor product space. So unlike pure states where we have a straightforward version of how symmetry acts on the state, so you have the unitary representation of your symmetry, which keeps the state invariant, or maybe you can generalize it to projective representations and so on. But in a mixed state, it can appear in slightly two inequivalent ways. So the first version is the usual generalization of our of the pure state version, where instead of U acting on rho, U acting on psi, we have U conjugating rho and keeping the state invariant for all group elements, of the symmetry group G. So this turns out this is equivalent to taking rho as a mixture of pure states with fixed, but possibly different charges under the symmetry. I'll give some examples shortly, but there is an equivalent way in which the symmetry can act on the system, where it is called the strong version, where U of G acting on rho gives me back rho with possibly with some complex phase. Okay, so this version is a strictly stronger version of symmetry than the weak symmetry, right? And it's a mixture of pure states with same charge. And these two different versions can have very different physical implications, as we'll see. So the example that I started with was the SU2 symmetric spin chain, okay, it was not necessarily, the results will not necessarily depend on it being a 1D chain, but that's what the numerical result that I showed in the beginning. So let me study this in the context of SU2 symmetric or SU2 covariant states for some small number of qubits. So I can look at invariant pure states. So SU2 invariant pure states are some kind of some singlets. So I can think of dimerizing this 4 qubits in this 2 inequivalent ways, and I can allow also for crossings, and this at least in this version. And then there are these 2 orthonormal states, which are these are 2 are not orthonormal states, but you can form an orthonormal state, which is in the subspace. And if I think of any mixed state, which is a mixture of some state in this space, that would be called a strongly symmetric state under this symmetry. But now I can also think of some other covariant states under SU2. So for example, I can take one of these bonds and make it into a triplet. And then this would be a general covariant pure state. But now if I mix different covariant states of the symmetry, that would also be symmetric under the weak sense, but not under the strong sense. So that is the difference between strong and weak symmetry now. Okay. So going forward, this covariant pure states can be labeled in my tensor product Hilbert space in this particular way. So we first can label a particular pure state with its irreducible representation. Then if the irreducible representation is if there are many states in it, for example, if it's a non-Abelian group, then M can label the state within the irrep, and then alpha is the overall multiplicity label, which is telling you which of the subspaces of a particular irrep in my tensor product space is being represented, right? So the dimension of my irrep can be which is DJ, can be non-trivial if the group in this case is a non-Abelian group. So just to clarify, in this case, I'm talking about a complete zero-form global symmetry. There is no higher form version, at least in this notion. And one can maybe think of generalizing it, but I'm restricting myself to usual symmetry. So now one can, because I'm motivating how to go to channels and think about symmetry, so one should think about operators, and linear operators acting on H can also be decomposed due to symmetry. And these will generically be spanned by operators of this form. We consider, for physical purposes, operators with the same left and right charges, which span this Hilbert, linear space of which I label as B, G, J, M. So these are spanned by operators of the form this, where the irrep label and the state within the irrep labels are fixed on both sides, on both ket and bra, but the multiplicity label can in fact change. So the reason I introduced this notation is to evaluate the symmetric channel is such that the cross operator of the channel commutes with the symmetric group. So I have some representation of my symmetric group, so U of G, and all the cross operators are commuting with this, with this symmetry. So this is a natural definition, but one of the implications of this definition is that the strongest symmetric channel preserves both the J and M labels of my state and only mixes the multiplicity label. So this suggests that within each such subspace there will be some steady state, or there could be some steady state. So in general, there will be multiple steady states of this channel organized by the symmetry of the initial state. So I think this is a pretty standard story, which is not so surprising that because of symmetry there is some degeneracy. But now we have, instead of our usual way of thinking of the degeneracy of the Hamiltonian, we're thinking of the degeneracy of the channel. But many of the discussions can follow through. Right. So I just wanted to give you a little bit of motivation of why this is not such an unnatural thing to study. In principle, strongly symmetric channels can arise naturally when I connect my system to a bath that can interact with the system and exchange energy and other information, except for some symmetry resolved information. For example, I have some system and I have some environment, and it does not couple along some symmetry, but it can exchange some other information like energy, for example.
Excuse me.
And this can
even
ask
a question.
Yes.
Oh, sorry for the interruption. The concepts you introduced here about the strongly symmetric channel according to the system environment exchange sounds like that there is no charged operator exchange between the system and the environment. Am I right?
Yes.
Oh, thank you.
Yes. So yeah, that's another way of saying that. The environment does not know, the charge is preserved under the environment coupling. And
so it sounds like that the charge neutral operator can exchange between them, right? For example, for Z2 symmetry, the poly X operator can exchange between the system above, but the poly Z operator cannot.
Yes.
Thanks.
Yeah, and this kind of situation can arise even in natural quantum invariant systems with some of those more standard, system-based dynamics that you can think of coupling a Heisenberg Hamiltonian to some lattice phonons. Those naturally have the C2 symmetry in their coupling. And also you can generally think of other physical situations where this kind of symmetric coupling to the bath can be natural. But at this talk, I'm just going to assume that we have this kind of strongly symmetric channels and think about the implications. So let me first, this is the first result that we can share from this construction, is that I discussed that how the linear operators or the density matrices in my because of the symmetry, it kind of decomposes into different sectors, and a theorem that we can prove is that for a strongly symmetric channel, there's always at least one steady state within each of these subspaces. In principle, there need not have been any steady state, but because of the structure of quantum mechanics, we can always guarantee that there is at least one steady state. And furthermore, if the Krauss operators have some more properties that they form a complete algebra of symmetric operators, we can show that the steady state is unique. So in some sense, completeness of my channel leads to a unique steady state within a particular symmetry sector. So now we have basically, this is not a necessarily and sufficient condition. This is a sufficient condition to say that there is a unique steady state within a symmetry sector. So we have basically said that removed all degeneracies except for those coming from symmetry, if I consider a channel that has this particular property, which forms a complete algebra of symmetric operators. So I don't want to go to the proof of this theorem, but this is something that you can prove just from the simple linear algebra and properties of quantum mechanics. But an important lemma that will be relevant to describing the result that I shared initially is that if the channel is unital, which, if you remember, it preserves the identity matrix, and complete, which is the condition relevant to this theorem, then the maximally mixed state within a particular symmetric sector would be the equal mixture of all the allowed states. And because I introduced this basis of symmetric states, I can just think of the equal mixture of all such states within my symmetric sector. And these are just labeled by the different multiplicities of my symmetry. So this is the state that I'm looking at. And just going back to the numerical experiment that I showed, one can show that this satisfies all the conditions of the theorem. So we have, the channel has this completeness properties, and the initial state is also in the invariant sector. So the steady state there's a unique steady state, which is just a mixture of all such, in some sense, all the singlets. Right? So one can ask, is this state entangled? So is this state as a mixed state entangled? So to answer this question, one has to think a little beyond, a little more about what it means for a mixed state to be entangled. So doesn't immediately follow from the definition of pure states, but one can think of a mixed state to be entangled if it cannot be interpreted as a mixture of product states. So I'm imagining in this context, I'm just imagining some bipartite decomposition of my Hilbert space. And if my density matrix cannot be written down as a mixture of product states between the parts A and B, then this is a legitimate definition of entanglement. But this is a somewhat unsatisfactory definition because it's a negative definition, right? So I have to, in principle, I have to look for all pure state decompositions of my mixed state and check for all such decomposition whether it can be written as a mixture of product states, and it's typically very difficult to do. But regardless, from an operational point of view, this is a very well-defined property, and this is something that operationally has a meaning. So this is a definition of a state being entangled, but we want to check how much entangled is the state. So one has to have some measure of entanglement. And so there are two ways of thinking about this coming from entanglement theory. One is something called entanglement of formation, and the other is called entanglement of distillation. So let me describe entanglement of formation. So imagine you and some alien are want to produce this density matrix. Then one definition of a measure of entanglement would be how many Bell pairs do you need to share such that any local operations and some maybe classical communication can allow you to make this state. So this is basically the number of amount of entanglement you need to form this state with just local unitary operations and some classical communication, right? On the other hand, I can have a different notion of entanglement, which is suppose you and an alien you already have this density matrix, and you can ask how many Bell pairs can I distill out of this density matrix just by using local operations and classical communication. So these two notions, though operationally different, give the same result for pure states. This is a central result in entanglement theory, that both of these asymptotically, in some concrete sense, equal the von Neumann entropy of the reduced density matrix of my system. So this is the reason why we just often just use von Neumann entropy as proxy for entanglement, because it equals this operational meaning. However, for mixed states, these two quantities are generically different, and one is a weaker form of entanglement than the other. Basically, entanglement of formation tells you how many Bell pairs you need to form that state. So, and entanglement of distillation tells you how many Bell pairs you can get out of that state. So you should have some kind of hierarchy between these, and that's exactly what happens. That you can't get some free entanglement out of just using some LSCC process. So entanglement of formation will always be strictly larger than the entanglement of distillation. So let me describe this a little more. So any mixed state can be non-uniquely decomposed in terms of pure states. And we want to define entanglement measures, which are convex optimizations over all such pure state decomposition. So the entanglement formation, recall, is the definition. The definition asks for minimum number of bell pairs that you need to prepare the state. So I can have a particular decomposition for which I can take, that average of the entanglement shared between A and B, and now I have to minimize over all such pure state decompositions. So this will give me my entanglement of formation. And similarly, entanglement of distillation is in some limiting sense, is the number of bell pairs you can get out of some LOCC protocol, which is this distillation protocol. So this is just this expression just formalizes the notion that I already described before. And these measures satisfy the relation that distillation or distillable entanglement is strictly smaller than entanglement formation. Now, this is all very good as definitions, and people have studied different properties of these entanglement measures in quantum information theory. But one thing that you can already guess that from these definitions, these are extremely difficult to compute for any realistic quantum state, because you have to have some optimization over different decompositions of many body pure states. And even computing entanglement for a single pure state can be difficult, but now you have to optimize over all the different ways in which you can represent your mixed state over this decomposition. So these are typically intractable, and we don't really know examples of many body mix. We didn't really know examples of many body mixed states for which these quantities can be computed. What I will show you is that this particular very special class of states that we are considering turns out that you can compute all these measures exactly and using some algebraic tools. That will be the next set of results. But before that, I want to also mention another, you might have encountered another measure of entanglement in mixed states, which is the logarithmic negativity, which defines something like you take the density matrix, you take a partial transpose over part of it, and you measure the log of the one norm of this transformed density matrix. The point is, the reason why this is an entanglement measure or an entanglement monotone is that separable states have this property called positive partial transpose, but entangled states don't have the property. So by saying how non-positive this partial transpose is, you can compute some notion of a measure of entanglement. And one of the reasons why it's useful is that it's an upper bound for the entanglement of distillation that I defined before. But more importantly, this is, in principle, it's a computable definition, right? So you give me your density matrix using some reasonable computational complexity, I can compute this object. But there's some problems with this entanglement negativity. One of them being it's not faithful. The fact that some negativity can be zero does not mean that the state is non-entangled. Furthermore, it's not a very good measure of how much entanglement it is. There is no operational meaning to some state having higher negativity than the other state. There is no reasonable operational meaning to this. So these are something that you can compute, but in general, these are you have to always remember the caveat that these are not faithful measures of entanglement. Okay, but this is a kind of a detour into entanglement theory. But let's go back to our state that we are looking at, which was this maximally mixed state. And I want to specialize to even a further class of this maximally mixed states, which I call the maximally mixed invariant states. So this generalizes the mixture over all singlets in the SU2 case. So I look at the invariant representation of some symmetry group, and I mix over all such states in my tensor Hilbert space. Right. So for this particular state, we have this result that for any bipartition of the state, the entanglement of formation and entanglement distillation are equal and exactly computable. So I mentioned that in general, these entanglement measures have a hierarchy between them, but we can show that these two are equal. And not only that, we have an exact computation to show that these two things are exactly computable. And more interestingly, maybe from a many-body theory perspective, we have this kind of symmetry-based classification. So in particular, if the symmetry group is abelian, then we show that the entanglement is zero, so it's a fully separable state. there is no entanglement between any parts of the system. If it's a non-Abelian discrete symmetry, for example, S3 or some non-Abelian group, but it's a discrete group, we have some entanglement between different parts of the system. It's an order 1 entanglement, so it's not a completely product state, but it's an order 1 entangled state. However, for these non-Abelian continuous groups, which are described by some Lie groups, in particular semisimple Lie groups, we can prove that these entanglement measures have at least logN scaling, and we'll actually have a complete expression for this thing. Right. So I guess, yeah, this is the result, and I want to sketch a little bit of the proof, but do you have any questions at this point about?
I have a question.
Yes,
so
please.
Does O2 belong to the non-Abelian continuous case?
No, it's not. Yeah, it's not a semisimple group, so it doesn't satisfy the, like, it does not have. We can't. The result depends on it being semisimple because there are some properties of the group that we use to argue this. So O2 does not have that. It has two distinct subgroups. Right?
Yeah.
So
for O2, it belongs to the second case.
Yes.
I see. Thanks.
Although, yeah, I think it belongs to the second case. Yeah. Any further questions? Okay, so let me go ahead. Right. So I want to, maybe briefly give you a sketch about how to prove these statements. But the important point is I just want to convey this physical context of physical meaning of this result, and the proof will try to motivate some of this result, but maybe not give a complete proof. Right. So the idea is to basically look at representations of these groups, and remember we have this mixed state, and I want to compute these entanglement measures, which are optimizations over different pure state decompositions. So I want to, in some sense, provide an optimal decomposition of this mixed states, so that the mixed state as a mixture of these pure states will give me allow me to compute just the entanglement measure just by looking at the pure state itself, right? So that's the goal that we're going forward. So we have this tensor product space of say n qudits, which each of them are some irreps of the group. And I have some bipartite decomposition of the Hilbert space, say A and A complement, and just by using simple representation theory, I can decompose each of this part into its irreps of the global symmetry, and this is in terms of the multiplicity of this group in this Hilbert space. I have this particular decomposition. So one particular property of the invariant state, because recall the invariant state is a trivial representation of my group. It turns out that for all semisimple Lie groups and discrete groups, these are multiplicity free, in the sense that if I am able to distinguish in each of the parts which of the multiplicity spaces my states are in, I should be able to distinguish an unique invariant state between these two parts. So this is captured by this algebraic equation. In the sense, so on the left, I have the multiplicity of all invariant states in the total Hilbert space, and on the right, I have the multiplicities of different irreps of J and J star, which is the dual representation on different parts of the system, and I have this property which just follows from representation theory. But one consequence of this is that for each pair of such irreps, which form a global invariant state, I can construct an orthonormal singlet state. So I should think of each of my part of the system has some representation, is carrying some representation, say J and J star, and I can form a global singlet by combining these two states in some particular way. And let me just denote that state by JJ star. So think of like, if the total, if I take my SU2 symmetric system, I take a part of the system which is, which is carrying some spin half representation, and the other part also is carrying some spin half, and now it can form some singlet between these spin half states, right? And all the different singlets that I can have between A and B, between the parts A and A complement, are basically labeled by the different multiplicity spaces of these individual irreps on each side. So for each of these, so I can think of spin half being represented in many different ways on some part of my system, and spin half being represented in some other different ways in the other part of the system, and I can form singlets between them. So this gives, because of the completeness result that I showed, this gives a complete orthonormal basis for all such globally invariant states. But the important point is that now I have a particular decomposition of my maximally mixed state in terms of these singlets. And what will turn out that these are actually optimal in the sense that for such decomposition of my mixed state, I can compute these entanglement measures, and these two, this will give me the correct answer. So for that, we have to have some physical argument. And the argument is that, I have represented my mixed state as a mixture of these global singlets because it's a particular decomposition. And remember, the entanglement of formation was a minimization over all such decompositions. So this particular decomposition gives me an upper bound to the entanglement of formation, right? So what I can do is I can just take the average of the entanglement between entanglement shared by singlets, and we know what the entanglement shared by singlets are. And so we can compute some upper bound to the entanglement of formation. The tricky part is that we can also show that this particular decomposition also gives me a lower bound to the entanglement of distillation. And there you have to use some quantum informational tools, in the sense that if I have a singlet between A and B, I can just measure locally what is the representation and what is the multiplicity on each of the parts. And by that, I can already distinguish between the different singlets, right? So this is, if you think about it, that is a completely good distillation strategy that allows me to distinguish between the different singlets shared between the two systems. Okay. So the proof is that I have a particular upper bound to the entanglement of formation, and now with this distillation strategy, I have a lower bound to the entanglement of distillation, and I just sandwich them, because these two being equal means that the entanglement of formation and the entanglement of distillation are equal, and there's just the average number of singlets between these two different sides will give me the entanglement measure. So if it was not completely clear, maybe it's not so important, but the result that we have is that, you have a completely closed form expression for the entanglement of formation or the this level entanglement between any two parts for such particular mixed states. Okay, so and then it's given in this form. The important thing that I want to just highlight, and these are completely determined by some properties of the group and its representation in my Hilbert space, right? So dj is the dimension of the Hilbert space, dimension of a particular irreducible representation in my Hilbert space, and these c's are those multiplicity labels, right? These are some Clebsch-Gordon series coefficients, if you'd like, for a particular representation. So what do I gain out of this? But the point is that just by looking at this expression, you get these results that, because all the dimensions of all the irreps of abelian groups are trivial, so you have this order. So you have entanglement being exactly 0. That means that it's a separable state. And for the other cases, we have some non-trivial, structure. And if you work a little harder for these semisimple Lie groups using some character theory story, which maybe I'll skip, I can actually get a closed form expression for entanglement of formation for semisimple Lie groups. So it's given in this way, which is in terms of these algebraic quantities, which is the dimension and rank of the Lie algebra for the group. But the important thing is that you find that this entangled formation has this log n scaling, where n is the number of system, right? Number of qudits. And in this particular formula, even though the previous formula was completely general, this formula is just is specialized to a half system, because we need to see how many ways these different irreps are represented on part of the system, and it helps to compute if I consider half of the system. But in principle, we can plot this and see how it behaves for any bipartition. So this is the result that motivates this symmetry-based classification. So as you can see that this particular when the symmetry group is non-Abelian continuous, and like SU2, SU3, any SUD group or any SOD groups, we find that this the steady state is highly entangled because it's scaling. It's in some extensive fashion. It's scaling. The entanglement measures are scaling. So we can characterize a lot more properties of this state. In fact, we can study like the correlation structure of the states. Let me briefly mention that as well. So in particular for the SU2 invariant steady state, you can compute like what is the some correlation, say like S dot S type correlation for some distant qudits. And because it's this completely invariant maximally mixed state, you can very easily find out that the correlation has this algebraic behavior as 1 over n, right? So if I have n qudits, the correlation between any ith and jth qudit, it has this 1 over n behavior. Now, because of this 1 over n behavior, using some Lieb-Robinson arguments, you can show that this state cannot be prepared in some order 1 time or some constant time using some local channel, because the tails of the Lieb-Robinson bounds has exponential decay, but now because I have this algebraic decay of correlations, I necessarily need a deep circuit to be able to prepare this state. So what it tells you is that not only is this it was kind of obvious from the entanglement measure, because the entanglement measure being large implies that you have to have a large depth preparation, but also this was also clear from the correlation structure of the state. The correlation being algebraic means it's a non-trivial state. On top of that, we have this, yes?
So what kind of Lieb-Robinson bound are you using? Is it for channel or for Hamiltonian?
So for local channels, you can have a Lieb-Robinson bound, right? Like, so with local channels, you bring in some ancilla and you apply some local unitary gate. Because the ancilla, if you assume that they are all applied locally, the same Lieb-Robinson bound for Hamiltonian or will apply for even for local channels.
Mm-hmm.
As long as you don't allow for any kind of non-local classical communication between the different parts.
But if I allow local classical communication, does it speed the things up?
You mean non-local classical communication, or
local, just local?
Oh, with any local communication, it will still have this Lieb-Robinson arguments will apply.
But if I have local feedback to control what kind of channel, what I should apply after one step, does it speed up things?
It can only speed up towards some constant level, unless you also have this global classical feedback. Maybe you, like for example, a simple example would be you measure some Z to symmetric fashion. Then you look at the parity of the measurement outcome and then apply something. But that's a global thing, right?
I see. So for the global feedback setup, Andy Lucas and Chao Yin, they had some paper on the speed bound, right? Do you apply that bound? What do you get?
Right. So actually, like I have even without applying that bound, I think that bound gives you something. Let me think about this. I think that bound might mean that for global adaptive circuits, it might give for this kind of systems, it might give you an order one time lower bound. It has to be at least order one time to prepare the state, but that's not very useful. But actually, we have an argument in our paper that any adaptive protocol will take at least log n scaling. And that comes from the entanglement structure and not from the correlation structure. Because we also have this like stronger result about the entanglement and not just the correlations. We have an argument by looking at some entanglement methods like entanglement purification that even global adaptive circuits will require at least a lower bound of log n depth.
I see.
I think that's an interesting point from the correlation structure.
Thanks.
So yeah, this is the kind of the slogan that I want to convey here, that if I look at some local density matrix of the state, it's completely trivial, but it's globally highly non-trivial because there is this global entanglement between them. This kind of reminds you of like topological order and things like that, but this is maybe a very simple version of symmetry enforced entanglement. Okay, so let me go back, to give some further motivations for quantum many-body theorists. So I gave this example. I showed you this example where the steady state of the unital steady state of these unital channels are highly entangled, and these steady states are these maximally mixed states within particular symmetry sectors. So I can think of that as being the infinite temperature Gibbs state when I restrict myself to a particular symmetry sector, right? So there is this global restriction which restricts me to a particular symmetry sector, and now I mix between all states that are accessible within that symmetry sector. So that smells a little like a Gibbs state, but at infinite temperature. Now one can ask, what about what happens to finite temperature, right? Like I can imagine I have this setup that I discussed before. Like I have a system which is connected to some bath at some finite temperature T, but now there is it doesn't allow you to exchange any symmetry resolved information or symmetry charge, right? So then under some general arguments, you can argue that the steady state would be the Gibbs state, but now projected down to some symmetry sector, right? So what our results tell you is that at the beta equal to 0 limit, that state itself is also a very interesting state. It has some long range entanglement, but one can ask like what happens at some finite temperature, because that's a more maybe a little more physically relevant case. And it is very difficult to and the motivation behind that is like I told in the beginning that there are these different scenarios that can arise when I have a system that's connected to some environment, but there is another further system that I can consider where the bath has some symmetry restriction, right? So then I can look at a thermal state instead of a steady state of some channel. I can look at a thermal state within some symmetry sector. And and we don't have a very good understanding about what happens at finite temperature. We have a conjecture with some non-proof in our paper that for local Hamiltonians, when you have some local structure, then the strongly symmetric thermal states at infinite temperatures have these properties that we studied. But at any finite temperature, where temperature is it's not order n, this entanglement of the subregion gets cut, provides a length scale that cuts this entanglement off. This kind of reminds you of what happens for CFTs, but at 0 temperature, where if you put some scale, then that scale cuts off the logarithmic scaling of entanglement. So this is a conjecture, and we don't really know how to prove this for beyond the infinite temperature limit, which we already discussed before.
Question?
So
so if the temperature is negative, how does this conjecture modify? What does it modify?
Talk about that. That's a good question, but I have to think about that. Yeah, I don't really have anything to say here.
Thanks.
Right. So yeah, so let me, I think, oh, sorry, I'm already quite out of time, but let me just summarize these results. So we have this result about how strongly symmetric channels can have these highly entangled steady states, and we have the symmetry-based classification. Maybe there is some interest, just to point out some interesting directions. I mentioned already this finite temperature. What happens at finite temperature is open. I think just a more, I gave a very mathematical, proof of the entanglement structure and so on. It'll be interesting to have a more, physical description of why the steady states are, the symmetry restricted states are highly entangled. And one can definitely look at other, directions of like looking at generalized symmetries, and a quantum informationally motivated set of questions is people often use Gibbs states of local Hamiltonians as being a tool for showing some quantum advantage, right? Here we show that the Gibbs state with a particular symmetry restriction can be highly entangled. So it's interesting to ask questions of what are some quantum informational implications of this result. And I think those are highly, it will be interesting to explore for future. So with that, yeah, I thank you for your attention, and yeah, I can take any further questions.
Okay, thanks for the very interesting talk. Any questions? Yeah, maybe let me ask a question. Here, when you say robustness, what kind of robustness do you mean? Under what kind of perturbation?
Right. So we don't expect this to survive if you break the symmetry. So because this is like a highly, this is a completely symmetry protected phenomenon. But one can ask like, so I restricted myself to unital channels, and for the unital channels, I could show that the steady state for any unital channels, the steady state is this maximally mixed state. But I can have non-unital symmetric perturbations to my channel, and that will kind of generate some states like the finite temperature state. It will not mix up exactly equally among all the states, but it can produce some states with higher weights, somewhat like these thermal states. Then one can ask, like, for such perturbations, is this entanglement robust? So we have some numerical indication that it is robust to such perturbations. It doesn't really, it can change the profile of the entanglement a bit, but it doesn't change the scaling. But it's difficult to establish it because numerically you can only compute things like negativity and for very small systems.
May I ask a question?
Yes,
yeah,
sure.
It seems that you are considering something like a maximal mixed state within a fixed charge sector. But according to our previous study, let's say the spontaneity of so-called strong to weak SSB, if you perturb the system by some local symmetry breaking channel, you know that the only information restored in your ensemble, that is a charge sector fixing, has been completely destroyed. That is exactly what the term spontaneity means. It basically means the local perturbation can lead to global change. So what's going on in your entanglement measurements? It seems that there will be a if there will divergent perturbation.
Yeah, I think that's an interesting point. I haven't thought about that. But one thing that just to relate to the strong weak SSB, one can show that these are examples of the strong weak spontaneous symmetry breaking.
Yeah.
And so with that, we can argue, like, for example, this correlation structure is stable under symmetric perturbations. But whether the entanglement structure is also stable to the symmetric perturbations, we don't know.
I understand. I basically could imagine what's going to happen under the symmetric perturbation. But what about the symmetry breaking perturbation?
Right. So you're asking if there's some kind of susceptibility
Yeah,
to
something like
symmetry breaking
a
perturbation.
entanglement and susceptibility. Yeah,
Right.
something like that.
I think that's a very interesting question. I don't really know. So, I mean, naively, it seems that it's possible because at the singular limit, the entanglement is extensive. Like it diverges. So yeah, so I think it's a definitely an interesting possibility. But the one difficulty is that to compute mixed state entanglement measures for any reasonable many body systems is very difficult.
Yes, of course.
Yeah. So we can compute things like negativity, and maybe that can already give us some sense of the susceptibility of entanglement, but we haven't done that.
Sure. Thank you for your answer.
No worries.
Jiahao, can you explain the question again? You said some local perturbation can induce some global change. What?
For example, let's consider 1D qubit system with an Ising symmetry. Let's say the product of poly X. You know that within the charge even sector of the Pauli symmetry, the maximal mixed state is literally the 1 plus product of X. It's the simplest example of strong to weak symmetry breaking. And then in our previous paper, we proved that if you perform a single Z measurement on only one site, even in the thermodynamic limit, the resulting density matrix could be the maximally mixed state. Should be, not could be. Should be the maximally mixed state just equals to 1, not the 1 plus X. Okay, so you know that the change from a 1 plus X to identity is a global change by a local perturbation. It's pretty much like an analog to the pure state. That if you consider a Cas state, let's say the quantum superposition of all up and all down in the thermodynamic limit, if we apply an external magnetic field along the Z direction, even if we only define this external perturbation on only one side, the resulting state could be either all up or all down. Depends on the side. Depends on the sign of your external perturbation. So that's the spontaneity of the SSB in the sense that a local perturbation can lead to global change of the whole system. And what the meaning by global change? In the sense that the global change can never be restored or recovered by any local operation. For example, for our previous example of 1 plus X under Z measurement, this process can never be recovered by another local channel.
I see. Thanks. Any other questions? Okay, if not, I think we can stop here. Subhayan, thank you, and thank everyone for coming. Bye.
Thanks, Adrian. Yeah, great to see you again.
Yeah, good to see you. Bye.
Recording stopped.